on some free graphs. So please.
Yeah. So thank you very much. So yeah, I'll talk about absolutely continuous spectrum of substitution trees or trees with finite forward cone type. So I guess I chose the shorter title here. And this is joint work with Daniel Lenz and Simone Warze from Munich. So what we're going to do is, here is a plan. Like, we start with a definition of substitution trees and introduce the model, and I will draw some pictures. Then introduce some operators and prove or show you the results about absolutely continuous spectrum for the free operators. And then we're going to study perturbations of those operators for some deterministic potentials and for some random potentials. And I don't know if we get to the ideas of the proof, but so it's on there. So let me try to convince you why it's interesting to look at these trees. And the first reason is on the interplay between geometry and spectral theory. So you might ask the question, like, how does the geometry affect the spectral? How does the geometry affect the spectral theory of an operator? Or also, like, how much regularity you need to prove absolutely continuous spectrum? The second motivation comes from spectral theory itself. So recently there have been like a lot of results in one dimension for Jacobi operators showing that you can easily destroy absolutely continuous spectrum. So there are results of Remling, who say like every potential which is not reflectionless destroys the absolutely continuous spectrum. Or Yoram Lars has some examples for like decaying potentials which decay very fastly and destroy the AC spectrum. So, and for our trees, which because of the loss of regularity we have in this model, it's totally different. So we show like very stable AC spectrum. And the third reason comes from mathematical physics that was Ivan Veselic already mentioned. In dimension 3 and higher, you expect under random perturbation or small random perturbations that you have some persistence of AC spectrum, and this behavior can be observed in the case of trees, which is sort of an infinite dimensional analogon. So to give you an idea of the trees we are talking about, I give you an example, and as I said, it's a substitution model. So so we have a label set. You can think of like a black vertex and a white vertex, and a set of rules. The black vertex goes into having one white black forward neighbor and one white one, and say the white vertex has two black forward neighbors and one white. So this gives you two trees, two infinite trees, in the following way. So if you start with a black vertex, then you apply the substitution and get this. Then again, here I have a black vertex, so you apply the substitution, and for the white one it's above, and that's the way you continue. So you get 2 here, 3 here, and that's the way you continue. And you can play the same game starting with a white vertex, applying the substitution the first time, and then you go on like this. So that's the idea, and that's like like one of the main examples you should keep in mind. And I want to give you now a formal definition for this substitution rule. So your input data is a label set, which is denoted by alpha. It's finite, it's a finite label set. And the second input is a substitution matrix, which is a mapping from A times A into the natural numbers with 0. And now let's denote the label by J. We inductively construct a tree denoted by TMJ as vertex set Vj and edge set Ej in such a way that we say that the root carries the label J. That's how you start your induction, and then say every vertex with label K has MKL, so that's the MK value of the substitution matrix, forward neighbors of label L. So let me give you some more examples to see how. I will come to this in a minute. So that would be the second example, but let me start with a much easier one. If A is just a one element set, then M is just a number. So, and if K is equal to 1, then you obviously have the half line. And if K is equal to 2, then you get the binary tree. So as you have always K forward neighbors of the same type. The second example is, as Uzi suggests, the Fibonacci tree. And there you have two labels and the following substitution matrix has 3 1s and 1 0, and there you get two trees. So now we have like, if say that's the row for the white one, then you have one white forward neighbor, and then you have one black one and one white one. So that's you see that's for the white, that's the black. No, wait a minute. This way. So yeah. And why is this called the Fibonacci tree? As you see, like if you count the number of vertices in each sphere, that's the Fibonacci numbers. And this tree was originally studied by Florina Halasan in her thesis, and there's also a paper on the archive where she studies the Laplace operator and a random potential. And Another example to recover the one which I've drawn to you in the beginning is also you have two labels, and let's call this MF as M Fibonacci or M Florina, and let's choose M to be MF squared. Then you have this matrix, and as you can figure out, that gives you the tree which I've drawn up there. And this can be considered as like the two-step Fibonacci tree. And to give you another motivation, why it's worth looking at these objects is that you can actually show nice pictures. So they come up as spanning trees of hyperbolic tessellations. So that's a hyperbolic tessellation in the Poincare disk. So you can think of these squares to be regular, but as you like in hyperbolic geometry, you can't draw them in the plane. So you can think like 4 squares meeting in one vertex. And now if you start systematically to remove edges, you get a spanning tree. And as you see,
are all those edges supposed to be the same length?
yeah, all these edges are like in the proper metric.
And they're supposed to be centered?
Yeah. So so that's like a regular hyperbolic tessellation. And now if you like remove these edges, you see that actually this two-step Fibonacci tree appears here, here 5 times, and you glue them together in one root. So that's another motivation to study these trees. Good. So I have introduced the geometry, and now I'm going to introduce the operators. I want to talk about, and I will look at the L2 space of the vertices. So for every tree I get, I have a vertex set, and I look at the L2 space, and I look at operators Laplace plus, that's a small or lowercase v, and my Laplace operator here, for simplicity, I look at an adjacency matrix. But like you can pretty much take every difference operator you like, as long as it's compatible with the underlying tree structure. So you can put weights on it, you can study like really differences. So that's just for simplicity. So maybe it's a good point to give some references. So these models, they are related to so-called trees of finite cone type. So a tree of finite cone type is a tree where when you pick one vertex and you look at what is around it, then there are only finitely many versions of it. So like there are only like finitely many different vertices. And those trees, they were studied in random walks by Takac, Versnag-Nebeda, and people from Fractals, Grön and Teufel, and Merez. And what we have are sort of like directed versions of these trees of finite cone type. That's why in the original title I called them trees of finite forward cone type. So you have like a rooted tree.
So you don't subtract the this.
I could do it. I just don't do it for simplicity here.
Since the degrees are different. So
Yes.
the
So
same
I can allow for a potential which is the same at each vertex type. So this assumption to study the adjacency matrix is just like to make formulas more easy. But as I said, like you can study also this difference operator as you're probably like. However, you have to like impose some derivative boundary conditions at the root. So that might be a flaw, but that's only rank 1 perturbation. So then on trees, there were like people interested in rendering Schrödinger operators. So there are these results of Klein from the 90s, and then Eisenman, Simpson, Warzel studied regular trees, and they and Fröse, Hassler, Spitzer as well, and they all proved absolutely continuous spectrum. That this absolutely continuous spectrum is stable under random perturbation as long as the perturbation is small enough. But these are all the results for regular trees, and Florian Hallersan, she was the first like to introduce a model where the tree is not regular and proved the stability of AC spectrum. Like and the trees she studied were essentially like a sample 2. However, like you could allow for more vertices of this type in between. So that's like one special case of she studied. And then there's like early work of Aomoto, who studied trees with a underlying group structure, and he could exclude eigenfunctions. And recently there are these works of Breuer and Frank, where they showed that for radial symmetric trees, absolutely continuous spectrum is rare. So you need very strong assumptions on the regular or like the radial symmetric trees to get AC spectrum. So so let me come to the second point and talk about AC spectrum. And here I need some additional assumptions on my substitution matrix. And the first one, which I call M0, is simply that M is not the number 1. So I want to exclude the one-dimensional case. So that's just for simplicity. The second thing is that I want that M has positive diagonal. So if you look at the examples up there, so the binary tree is still in the game, but this Fibonacci tree drops out since we don't have a positive diagonal. But that's not so bad, as Florina studied this object already. And the third assumption we have is that M is irreducible. And irreducible means that there exists natural number n such that m to the power n has positive entries. So what does that mean? It means that in the tree you find every vertex type in the future of every vertex type. And that's a very natural assumption, since otherwise you can decouple the trees and study them separately. So so under these assumptions, we can prove the following theorem. So first of all, the operator, the free Laplacian, has the same spectrum on PMJ for all j. So no matter which root you're starting with, you get the same spectrum, and that's pretty much easy to see, as we have this irreducibility, so every vertex lives in the future of it, so also its spectrum should be in the spectrum of the Laplacian.
So no assumptions about V?
Oh, that's just for the free operator. That's the. I come later to, like, of course, if we study like perturbations of it, we have to put assumptions on V. But that's just the free Laplacian.
What did you say was the boundary condition that
Like you have to render your difference operators such that at every vertex of the same type it looks the same. So if you have like a white vertex here, it has like a backward connection, but this one, the root, doesn't. So you have to somehow impose some backwards direction by a boundary condition, meaning adding a potential of 1, let's say. So that's only for the case 2. It's not necessary for the adjacency matrix, since it's zero diagonal. So that's okay. But if you have really this difference operator, then the vertex degree at the root is different from any other. So like you have to make this adjustment. But this like the first part of the theorem still holds. Well, no, you might get an eigen. Like for this Laplacian, I wrote down, you don't have to impose any other boundary conditions. That's why it chooses. And the spectrum is purely absolutely continuous and consists of finitely many intervals. So that is just the warm-up part to say, okay, we don't have to care about which vertex we are starting with, but the actual statement is that the spectrum of the Laplacian is, the free operator is pure AC and consists of finitely many intervals. Because like whenever we want to study perturbations, we have to make sure that the free operator at least has a pure AC spectrum. And like the proof, uses we analyze the green function of the root. So defined as the matrix element of the resolvent, and which is given as the Borel transform of the spectral measure with respect to the root. So that's the root vertex, and for every label I have another green function. But since I have only finitely many roots, I have like finitely many functions, and one knows that by general theory that these measures converge weakly to the spectral measure. And what you do if you can show that the imaginary part of the green functions are bounded and they converge on some intervals, then you know that you have a density and you have an absolutely continuous spectrum. And for some cases, you can actually compute them numerically. What I've done to show you, so that is the like we chose like the two-step Fibonacci tree drawn here, and I've plotted the imaginary parts of the green functions in the limit, so that's the spectral density. So you see for this tree you have one interval reaching from here to here, and you have that's pure AC spectrum. So now you can ask the question, well, there is like one interval, that's what you know from regular trees. Like, is this finitely many, how rough is this estimate? Can it really happen that there is more than one interval? And there's an answer to this question. So, for example, if you also look at the adjacency matrix and now ask the 42, I didn't bother to draw this tree which has, then you see like you have again two green functions or two imaginary parts, and the one you don't see since it becomes really small on these intervals. But there you have your spectrum is here. And you have three intervals. So
Have you actually proved for this example that these three intervals?
I've like what you get is you can prove that you only have to compute the green functions for the roots, and then you have like by the recursion relation you have a system of polynomial equations, and you can reduce it by Gröbner basis, and then you have two polynomial equations of degree 4, and you can solve them numerically. So so like, of course, like you can solve them explicitly, but that would not be nice. So but that's like, yeah. Let me now come to stability. Of AC spectrum. And first we want to study certain deterministic potentials, which we call radial label symmetric potentials. And we want them to be bounded, okay, 0. So if you want to make them small anyway, and they have to satisfy the condition v of x equals v of y whenever x and y have the same label and same distance to the root. Oh, in this sense they are label symmetric and radial symmetric, and just draw you a picture. You have your tree here and in some sphere certain black and white vertices. So in each sphere all the white vertices have the same value and all the black vertices have the same value. And the same applies to every sphere. But like here and there, like these two black vertices can have different value. And also these two. Then we get the following statement. So let T and J be a non-regular tree. So there exists a finite set sigma naught in the spectrum of the free Laplacian such that for all compact I, so I can be an interval or any compact set actually. So for all compact I, there exists lambda greater than 0 that for all label radial symmetric V, which infinity norm is smaller than L, I is in the absolutely continuous spectrum of Laplace plus V, and the spectrum, this AC spectrum is pure. So let me illustrate in this picture. So maybe I take this one since. So Firm says there's a finite set sigma 0, so that's usually the band edges, and some additional vertices, which are in this case only 0. And then if you choose an interval I, you know that this is contained in the AC spectrum of Laplace plus V, assuming that V is sufficiently small. So, and here I had this assumption that T is non-regular, and this assumption is actually really essential, since the statement becomes totally wrong if you omit it. So let me put this down. The statement is wrong for regular trees. So in regular trees, radial symmetric potentials are actually radial symmetric potentials, since you only have one color. And then you know that Laplace plus V by this Salamiak-Fourier method, which was often demonstrated here, this is actually a direct sum of Jacobi matrices. And you know, for Jacobi matrices, you can destroy the AC spectrum very easily. Like, just take your favorite Anderson potential on the half-line, and you can destroy the AC spectrum of this operator. However, if you exclude the non-regular case, then the AC spectrum becomes very stable, which also shows that these are like really no one-dimensional models. There is a corollary which underlines the statement I made. So if we take T non-regular and we label radial symmetric such that V decays as, or like goes to 0, doesn't have to decay, it's just need to go to 0 as x goes to infinity, then we have that the AC spectrum of our Schrödinger operator is actually the AC spectrum of the free operator. And for all of you who know one-dimensional operators, know that this is also not sufficient for a Jacobi matrix. There you can have decaying potential to destroy the AC spectrum. But here we don't need any decaying restrictions how fast the potential has to decay. It's only that it decays at some point. And the proof is actually pretty easy. So this, since V decays, it's a compact operator. So the essential spectrum of this guy must be contained in the essential spectrum of the other one. And the other direction follows from the theorem, since you can exhaust the AC spectrum of the Laplacian by compact intervals. And then you get a lambda for each such intervals. And if you go far outside, then you see that this lambda is contained in the AC spectrum of this truncated Schrödinger operators, and by this truncation you don't change the AC spectrum as well. So in the remaining 5 minutes, I might tell you something about random potentials, that you can play a similar game with random potentials, and yeah, tell you what I mean by random potential. So you have a probability space and a random process from omega and the vertices give you the random value of a potential at the vertex x, and we need two assumptions, which are, first of all, if the forward trees of two vertices, if the intersection is empty, so if you have your tree and a vertex x here and a vertex y here, so the intersection of their forward trees, Vx and Vy, is empty, so we assume that they are independently distributed. However, if y is in the forward tree of Vx, then they might depend on each other. And the second is that if x and y have the same label, then the distribution on their forward trees should be the same. So the two examples I have in mind are the following. So the one is V is just IID. So then obviously everything is fine. So in the second one, you say V is an IID, random variable on the vertices, and then you define the omega of x as the sum over all vertices in the forward tree, and take the value of your IID random variable and you sort of weight it by such that the sum is finite. So in this case, the potential at x really depends on all values of the potential before. Right, and then can again write down a random operator, the Laplacian plus such a potential here. I put the coupling parameter in front of it, and a similar theorem holds. So there is a finite set sigma, which is the same as before, and for every, here called the IK, so for every compact subset of the spectrum minus sigma naught, there is lambda such that for all random potentials which satisfy these two assumptions, K is in the AC spectrum of a perturbed operator, and this AC spectrum is pure. So let me tell you like some possible extensions, what else you can do with this method. So like here we only looked at bounded potentials. So you can bounded random potentials. You can think of unbounded random potentials which are large with small probability. So such potentials were studied by Fröse, Hassler, and Spitzer, and also our method allows for those. The other thing is like you can allow small off-diagonal perturbations. So like put a random variable on the edges. That works as well. That sometimes goes under the name of first passage percolation, where they study transit times. And another interesting thing is random trees. So the first would be a percolation type model. So you take a binary tree and you are allowed to delete one of the forward edges by a certain probability. So assume the probability that you remove it is small. Then you should be able to prove AC spectrum of this object. And the other thing is multi-type Watson trees, but I'm happy to answer your questions after.